direction of the sign distance function. And by doing these two things, we can actually project our initial voxel position here onto the actual interface. And if we use this in this toy example here, see we get something that looks like this, but we get a much smoother representation of our interface. So if you do this on a 3D structure, we can use these methods to perform measurements of interface areas and also triple phase boundaries. So this is just one example, but this approach has been performed on an artificial example of two intersecting spheres. And if you want to calculate surface area, for instance, then we can just sum up all the polygons that separate the two specific faces that we actually want to do measurements on. And also, if you want to do calculations of triple phase boundaries, we can extract the triple phase boundary directly from our mesh as this connected line in our polygon structure. But you can see here that the triple phase boundary here is actually quite jagged. And also you can see over here that even though we use these subbox positions to actually obtain our initial triple phase boundary locations, it's still quite jagged here. But we can then, because we have this connectivity information in our triple phase boundary location, we can then smooth the location of these triple phase boundary points here to obtain something that looks like this, which is much smoother. So just a bit about the accuracy of these measurements. So this is kind of the artificial example I've been using for kind of evaluate this methodology. So, and here is an example of kind of two different kind of errors that we actually introduce or we want to avoid when we do this methodology. So the first error is the sampling frequency. So of course, if we use polygons to approximate, for instance, a circle, then the fewer polygons we use, the less surface area we get out from the surface estimate. So this is what this kind of structure here represents. And the second one is the sample accuracy. So how close are our kind of polygon vertices actually to the true interface locations? So this is what is represented here. So here's an analysis using this setup. So I have run this analysis on two intersecting spheres at the distance r between them. And then I changed the diameter of the radius of these two intersecting spheres. And then I calculate the triple phase boundary using the method I just described you, with this smoothing and locating the polygon structure. And I compare this value to kind of the true, or the exact interface boundary between such two intersecting spheres. And if you do this, then you can apply different numbers of iterations here. But for instance, if you do this for two smoothing iterations here, you can see that you can actually reconstruct the triple phase boundaries in such a toy example here at maybe 1 or 2% over segmentation in general. So here's just some example results or an overview of what we can extract of information from this kind of polygon reconstruction. So first up here we can extract, for instance, specific two-phase interfaces, and we can calculate the area of these two-phase interfaces. So not only for visualization purposes, but also to get quantitative measurements out of it. And of course we can plot or visualize our triple phase boundaries here. So this is just a video here showing two specific two-phase interfaces. So this is actually all the pore interfaces in a CTO and a C sample. So actually now I forgot which is what, but I think that the green structures here are actually the pore and the C interfaces, and the red structures here are the pore CTO interfaces. So it's just to visualize the kind of data you get out of it. And here's another visualization of the extracted two-phase boundaries. And I hope you can see that these triple phase bundles actually form these connected curve loops without any branching or other artifacts. Okay, so that was interface characterization. I will talk a bit about trying to characterize the network structure in our microstructure. So I'll use this toy example here to just explain what it is I'm actually trying to do here. So, for instance, imagine that this is a porous structure, and you want to send maybe some gas through this structure here. And what measurements would make sense to calculate on this structure? So one thing we could calculate was the shortest path tortuosity, which would just be the length of the distance or the shortest path through the structure, and then they compare that to the shortest path between the sides. And this ratio between these two lengths then give us this shortest path tortuosity. Another thing we could look at was the transport network thickness. So we could sample the thickness of this structure throughout our sample to come up with a distribution of these path diameters. We use this to identify bottlenecks as well. Another thing we could do is to identify these, or try to quantify these dead ends in the structure. So of course we might have some, for instance, a triple phase boundary down here if we have a connected phase. But then you can also do this analysis by treating the triple phase boundaries as like a source instead of just a dead end. And then finally we could also look at the size of cavities inside this network structure. So this is just an example of how to calculate a few of these measurements using this fast marching method, which is pretty much just a method of propagating distances throughout a structure. So for instance, if we have an artificial structure like this, much like the one I showed you before, and we want to calculate, for instance, the torch between this side here and this side up here, we can then use the fast marching method to propagate distances in our structure. So for instance, if we define a zero value down here, and then propagate distances out in our structure in all directions simultaneously, then the value we have up here actually gives us the shortest path to any location down here. So we actually have obtained kind of the distance of this path in our structure. And then we kind of compare this value we have up here with the value of the distance between our two sides in our structure. We can then obtain a tortuous measure at each location up here. And if we then do this at the entire 3D reconstructed volume, then we can get a distribution of tortuosities. Here's another example of calculating the path diameter throughout the structure. So here I can use the fast marching method to calculate a distance map, this time from the boundaries or the interface of the structures here. And so you see at any location here, the value here represented in the color coded here actually represents the shortest distance to the interface in the structure. And if we then locate kind of the centroid path through the structure here from one side to the other side, we can then sample the radius of our local structure here at this path here. This, if we extract all these values here, it actually gives us a distribution of the diameter in the structure. Okay. I think I'm almost done. Yes. I think yes. So here just some selected results from this network analysis. So this is actually an analysis of the path diameter in a LSC CGO electrode, and this has just been done on each of the faces separately. And I think it's quite easy to see here, for instance, that the pore face has a nice kind of narrow distribution of path diameters, but actually the LSC face has like a bimodal distribution. So we have both quite large path diameters, but also quite narrow path diameters. Another thing you can look at here is the dead ends in the structures.